In the darkness beyond Neptune, something stirs, not with consciousness or intent, but with the slow, inevitable momentum of celestial mechanics. The object designated 3I Atlas, the third confirmed interstellar visitor to our solar system, drifts inward on a trajectory that will carry it past Mars in the coming months. Its nucleus, perhaps 2 kilometers across, contains materials that formed around another star in another stellar nursery, perhaps millions of years ago. Ice and rock compressed in alien cold, now warming in the gentle pull of our sun's gravity. The comet's surface temperature remains locked near absolute zero, but instruments sensitive enough to detect the faintest infrared glow register minute fluctuations. These variations, measured in thousandths of degrees, represent the first whispers of solar energy penetrating layers of primordial ice. The warming occurs at a pace that makes geological time seem hurried. Molecules that have remained motionless for eons begin the subtlest of vibrations, a molecular restlessness that signals the beginning of transformation. Mars turns in its ancient orbit, indifferent to the approaching visitor. The red planet's surface temperature hovers at -80 degrees Celsius in the pre-dawn darkness of its northern hemisphere. Dust storms that once raged for months have settled into stillness, leaving behind rippled dune fields that stretch across plains wider than entire continents. The planet's thin atmosphere, barely a whisper compared to Earth's thick envelope, carries the faintest vibrations across rust-colored landscapes that have remained essentially unchanged for millions of years. Radio telescopes on Earth have begun tracking both objects with patient precision. The signals they detect from Mars arrive as electromagnetic whispers, data packets transmitted by rovers and orbiters that have been humanity's eyes on that distant world for decades. These radio waves, traveling at the speed of light, take between 4 and 24 minutes to reach Earth, depending on the eternal dance of planetary positions. The scientists who receive these signals work in quiet rooms filled with humming computers, translating cosmic static into images of ancient riverbeds and mineral compositions that tell stories older than complex life on Earth. The radio waves themselves become part of the narrative electromagnetic radiation that began as electrical pulses in human-built transmitters, converted to photons that race across the void at precisely 299,792,458 meters per second. They pass through the near vacuum of interplanetary space, carrying digital information about wind speeds, rock compositions, and atmospheric pressures. Some of these signals, scattered by Mars' ionosphere, continue outward toward the stars, bearing inadvertent messages about human curiosity toward distant worlds where no one waits to receive them. But 3I Atlas remains largely silent, too distant and too small to reveal its secrets easily. Astronomers know it follows a hyperbolic orbit, the mathematical signature of an object that will pass through our solar system once and never return. Unlike the elliptical paths of native comets, which loop around the Sun in predictable cycles measured in years or centuries, 3II Atlas traces a curve that speaks of infinity. It emerged from the void between stars, will briefly taste the warmth of our solar furnace, and will return to that same infinite darkness, carrying with it trace amounts of solar system material. The geometry of its approach reveals profound truths about cosmic motion. Its trajectory, when plotted on astronomical charts, forms a perfect hyperbola, one of the conic sections that ancient Greek mathematicians studied, without knowing they were describing the paths of visitors from other stars. The comet's speed relative to the Sun exceeds the escape velocity of our solar system, a mathematical certainty that ensures its departure. No gravitational embrace can capture this wanderer. It moves too quickly through space to be bound by stellar affection. The comet's silence holds mysteries that may never be fully understood. Did it form in the disk around a star now dead? has it wandered the galaxy for eons, a frozen time capsule carrying the chemical signatures of stellar processes that occurred before our solar system existed. Spectroscopic analysis suggests its composition includes water ice, carbon monoxide, and silicate minerals materials common throughout the galaxy, yet each grain potentially older than the Sun itself. These questions float unanswered in the cosmic dark, patient as the objects themselves. Mars completes one rotation every 24 hours and 37 minutes, only slightly longer than an Earth day. This fact seems almost impossibly convenient, as if the universe arranged for human sleep cycles to nearly match the rhythm of that distant world. But convenience has nothing to do with planetary mechanics. Mars spins at its current rate because of billions of years of gravitational tugs from the Sun and other planets, a complex dance of forces that has gradually slowed its rotation over geological time. The planet's day lengthens by approximately 2.3 milliseconds per century, an imperceptible drift toward longer nights and extended afternoons. The approaching comet knows nothing of such terrestrial coincidences. It has traveled for millennia in the absolute cold of interstellar space, its surface temperature barely above absolute zero. Now, as it draws closer to the Sun's warmth, that ancient ice begins the first stages of awakening. Molecules that have remained frozen since the formation of distant worlds start to vibrate with increasing energy. The process occurs so gradually that human instruments can barely detect it, but it represents one of the most fundamental transitions in physics, the slow emergence of a comet from its primordial sleep. Between these two objects, the familiar world that humans have studied for centuries, and the alien visitor that may never return to space, continues its ancient business of emptiness. Cosmic dust particles, shed by countless comets over millions of years, drift along gravitational currents, invisible to all but the most sensitive instruments. Solar wind streams outward from the Sun at 400 kilometers per second, carrying charged particles that interact with planetary magnetospheres in displays of physics too subtle for human senses, but perfectly recorded by electronic observers. The approaching encounter between 3I Atlas and Mars represents more than mere celestial coincidence. It marks a moment when materials from two different stellar systems will share the same region of space, their gravitational fields briefly influencing each other in ways too minute to alter either trajectory significantly. The comet will pass Mars at a distance measured in astronomical units, close enough for comparative study, but far enough apart to ensure that neither object disturbs the other's essential nature. This is how the universe conducts its most profound meetings, not with collision or drama, but with the patient crossing of paths in the vastness of space, each object maintaining its essential trajectory while briefly sharing the same corner of the cosmic dark. The comet designated 3I Atlas carries within its frozen nucleus a library written in ice and stone chemical signatures of a stellar system that may no longer exist. Its journey toward the inner solar system began not years or decades ago, but potentially millions of years in the past, when it was ejected from the gravitational embrace of its parent star by the chaotic dance of planetary formation. Since that ancient departure, it has drifted through the galaxy's spiral arms, a cosmic wanderer moving at velocities that make interplanetary travel seem leisurely by comparison. Astronomers estimate that 3I Atlas approaches our solar system at roughly 26 kilometers per second relative to the Sun, a speed that represents the comet's motion through the local standard of rest, the average velocity of stars in our galactic neighborhood. This velocity exceeds the escape velocity of our solar system by a significant margin, confirming beyond doubt that the object originated elsewhere. No gravitational slingshot maneuver around Jupiter or Saturn could accelerate a native solar system object to such speeds. The mathematics of orbital mechanics permit no ambiguity on this point. The comet's hyperbolic trajectory curves through space according to equations first derived by Johannes Kepler 4 centuries ago, when humans had barely begun to imagine that objects could originate beyond the sun's gravitational domain. Kepler's laws, formulated to describe the elliptical orbits of planets, extend seamlessly to describe the paths of interstellar visitors. The same mathematical principles that govern the motion of Mars also govern the passage of this alien wanderer, demonstrating a cosmic consistency that spans light years and eons. As theorize Atlas draws closer to the Sun, subtle changes begin to manifest in its surface composition. Solar radiation penetrates the outermost layers of primordial ice, causing molecular vibrations that have remained dormant since the comet's formation. Water molecules locked in crystalline structures begin to sublimate directly from solid to gas, bypassing the liquid phase entirely in the near vacuum of space. This process, called outgassing, creates an incredibly tenuous atmosphere around the comet's nucleus, a coma so diffuse that it barely qualifies as matter by earthly standards. The rate of sublimation remains almost negligible at this distance from the Sun, perhaps a few grams per second across the entire surface of the nucleus. This gradual awakening means that theorize Atlas will lose only a tiny fraction of its mass during its passage through the inner solar system. Most of its ancient material will survive the encounter intact, continuing its journey toward distant stars essentially unchanged. The comet serves as an inadvertent time capsule, carrying samples of its birth system toward regions of the galaxy it will not reach for millions of years. Radio astronomers track the comet's approach using interferometric arrays that combine signals from telescopes separated by thousands of kilometers, achieving angular resolution precise enough to detect positional changes measured in milliseconds. These observations reveal minute variations in the comet's trajectory caused by the rocket effect of sublimating gases, a phenomenon so subtle that it requires months of careful measurement to detect. The outgassing creates tiny jets of vapor that act like microscopic rocket engines, altering the comet's path by distances measured in kilometers over the course of its entire passage through the solar system. The chemical composition of these early gas emissions provides clues about conditions in the comet's birth system. Spectroscopic analysis reveals the presence of water vapor, carbon monoxide, and traces of more complex organic molecules, compounds that form in the cold outer regions of protoplanetary disks around young stars. The relative abundances of these molecules suggest that theorize Atlas formed in a stellar environment similar to the outer regions of our own solar system, where temperatures remained low enough for volatile compounds to condense into solid ice. Yet, mysteries persist in the spectroscopic data. Certain isotopic ratios in the comet's outgassing differ subtly from those found in native solar system objects, confirming its extrasolar origin while raising questions about the specific conditions that prevailed during its formation. The deuterium to hydrogen ratio in the water vapor, for instance, suggests formation temperatures slightly different from those inferred for comets in the Kuiper belt. These differences, measured in parts per million, represent chemical fossils of stellar processes that occurred before our Sun condensed from its parent molecular cloud. The comet's surface reflectivity, or albedo, measures approximately 4% darker than charcoal and similar to the carbonaceous material found in the most primitive meteorites. This extreme darkness results from billions of years of exposure to cosmic radiation, which gradually breaks down organic compounds and deposits a layer of carbon-rich residue across the nucleus. The dark surface absorbs solar energy efficiently, driving the sublimation process that creates the comet's tenuous atmosphere. Paradoxically, this darkness also ensures that most of the nucleus remains frozen, as the absorbed energy radiates away into space before it can penetrate deeply into the interior. Ground-based telescopes equipped with adaptive optic systems compensate for atmospheric turbulence to resolve details on the comet's surface as small as a few kilometers across. These observations reveal an irregular, potato-shaped nucleus with regions of varying brightness that suggest compositional differences across the surface. Some areas appear slightly more reflective than others, possibly indicating patches where subsurface ice has been recently exposed by small impacts or thermal stress fractures. The rotation period of 3I Atlas remains uncertain, as astronomers have detected only subtle brightness variations that repeat over intervals of several hours. The comet's rotation axis appears nearly perpendicular to its orbital plane, causing it to tumble through space rather than spinning like a top. This chaotic rotation may result from the gravitational influence of massive planets in its birth system, or from collisions with other small bodies during its journey through interstellar space. The tumbling motion will gradually change as outgassing creates torques that alter the comet's angular momentum. But these changes occur too slowly to observe during its brief passage through our solar system. Navigation specialists calculate that 3I Atlas will reach its closest approach to the Sun in approximately 18 months, passing just inside the orbit of Mars before beginning its long journey back to interstellar space. The gravitational influence of Jupiter and Saturn will slightly deflect its trajectory, adding a few kilometers per second to its departure velocity and ensuring that it leaves our solar system faster than it arrived. This gravitational assist represents an inadvertent gift from our gas giants to the interstellar medium, a tiny contribution of orbital energy that will carry the comet towards stars not yet born when it first began its journey through the cosmic dark. Across the ancient plains of Chryse Planitia, where Viking 1 first touched the Martian surface in 1976, thermal convection cells begin their daily dance as the Sun climbs above the eastern horizon. The temperature differential between the warming surface and the cold atmosphere above creates vertical columns of rising air dust devils that spiral upward with the mathematical precision of fluid dynamics. These whirlwinds, some reaching heights of 20 kilometers, carry microscopic particles of iron oxide and basaltic dust in lazy helical patterns that trace invisible highways through Mars' tenuous sky. The dust devils of Mars move with a deliberate slowness that reflects the planet's reduced atmospheric pressure. Where Earth's tornadoes can achieve wind speeds exceeding 300 kilometers per hour, Martian dust devils rarely exceed 20 kilometers per hour, barely strong enough to lift the finest particles from the regolith. Yet, what they lack in violence, they compensate in persistence. Individual dust devils can maintain their spiral structure for hours, wandering across the landscape like vertical rivers of suspended minerals, visible from orbit as dark tracks that snake across crater floors and ancient lake beds. The particles themselves tell stories written in geological time. Each grain of dust lifted by these thermal columns represents the erosion of rocks that formed billions of years ago, when Mars possessed a thicker atmosphere and flowing water carved the valleys that now lie dry and silent. The iron oxide that gives Mars its distinctive color formed through oxidation processes that required the presence of water vapor, a chemical signature of the planet's more hospitable past, preserved in every mote of airborne dust. Spacecraft orbiting Mars detect these dust devils as brief fluctuations in atmospheric pressure and electromagnetic fields. The charged particles within the spiraling columns create weak electrical currents that produce radio signals detectable by sensitive instruments. These electromagnetic whispers reach Earth as data streams embedded within the routine telemetry from Mars orbiters, arriving as ones and zeros that reconstruct the invisible dance of charged dust in an alien sky. The seasonal rhythm of dust devil formation follows the planet's eccentric orbit around the Sun. During the southern hemisphere's spring and summer, When Mars reaches its closest approach to the Sun, the increased solar heating drives more vigorous convection across the equatorial regions. The number of dust devils detected by orbiting cameras increases dramatically during these periods, sometimes reaching hundreds per day across the hemisphere facing the Sun. Yet, even at peak activity, the total amount of dust lifted into the atmosphere remains modest, perhaps a few tons per day, across the entire planet. Mars's thin atmosphere contains less than 1% of the mass of Earth's atmospheric envelope, creating conditions where the physics of convection operate at the edge of possibility. The atmospheric pressure at the Martian surface averages 6 millibars, equivalent to the pressure found 35 kilometers above Earth's surface, well into the stratosphere. In this rarefied environment, the formation of convection cells requires temperature differentials far greater than those needed on Earth. Yet the resulting air movements remain gentle enough that a human standing in the path of a Martian dust devil would feel only the slightest breeze. The dust lifted by these thermal columns eventually settles back to the surface, but not before traveling vast distances on high-altitude winds that circle the planet at speeds reaching 100 meters per second. Global dust storms, which occur roughly every 3 Martian years, represent the extreme manifestation of this process planet-wide events that can obscure the surface for months and fundamentally alter the atmospheric circulation patterns. During these storms, the normally transparent Martian sky becomes opaque with suspended particles, reducing solar irradiance at the surface by up to 90%. Radio telescopes monitoring Mars during dust storm seasons detect changes in the planet's radio emission patterns as the suspended particles absorb and scatter electromagnetic radiation. The storms create a form of natural radio interference that affects communication with surface rovers and alters the propagation characteristics of signals transmitted between Earth and Mars. Mission planners account for these communication blackouts when designing spacecraft operations, building redundancy into systems that must function reliably despite the planet's capricious atmospheric behavior. The microscopic composition of Martian dust reveals the planet's geological diversity in mineral form. Spectrometric analysis of samples collected by rovers shows a complex mixture of olivine, pyroxene, plagioclase, feldspar, and hematite minerals that formed through volcanic processes during Mars's early history when the planet's interior remained hot enough to drive active volcanism. The relative abundance of these minerals varies across different regions, creating a chemical map of ancient geological processes preserved in the dust that now swirls through the atmosphere. Some dust particles contain trace amounts of sulfur compounds that likely originated from hydrothermal processes, evidence that liquid water once interacted with heated rock beneath the Martian surface. These sulfates represent chemical fossils of conditions that may have supported microbial life, if such life ever arose on Mars. The particles now suspended in dust devils carry these tantalizing clues across continents, mixing materials from diverse geological formations into a homogeneous blend that obscures their original context. The electrical properties of Martian dust devils create phenomena that have no direct analog on Earth. The low atmospheric pressure and extreme dryness of Mars allow static electrical charges to build up on dust particles to levels that would discharge immediately in Earth's humid atmosphere. During large dust storms, this charge separation creates electrical fields strong enough to generate lightning, not the dramatic bolts familiar from terrestrial thunderstorms, but diffuse electrical discharges that occur within the dust clouds themselves. These electrical phenomena produce radio frequency emissions that Mars orbiters detect as sporadic bursts of electromagnetic noise. The signals arrive at Earth as brief interruptions in the otherwise steady stream of scientific data, electromagnetic signatures of electrical processes occurring in an environment so dry that static charges can persist for hours without dissipating. The phenomenon demonstrates how familiar physical processes, convection, electrification, and electromagnetic radiation operate under conditions so different from those on Earth that they produce entirely novel behaviors. Meteorologists studying Martian atmospheric dynamics have identified patterns in dust devil formation that correlate with the planet's complex topography. The massive volcanic formations of the Tharsis region create thermal anomalies that drive convection cells hundreds of kilometers from the volcanic slopes themselves. Similarly, the deep canyon system of Valles Marineris channels atmospheric flows in ways that enhance dust devil formation along specific corridors, creating preferential pathways for dust transport that have operated for millions of years. The interaction between surface topology and atmospheric circulation creates a form of geological-meteorological coupling that shapes the long-term evolution of the Martian landscape. Dust transported from the polar ice caps gradually accumulates in equatorial regions, while material eroded from the highland, cratered terrain settles in the northern lowlands. This process occurs at rates measured in millimeters per millennium, representing a form of planetary-scale sediment transport that operates on timescales comparable to continental drift on Earth. Radio waves propagate through Mars's tenuous atmosphere with a clarity that would seem impossible on Earth, where water vapor and dense air molecules scatter and absorb electromagnetic radiation across broad frequency bands. The Martian atmosphere, composed primarily of carbon dioxide at a pressure barely 1% that of Earth's sea level, offers minimal resistance to radio transmissions. Signals originating from rovers on the surface reach orbiting spacecraft with remarkable fidelity, carrying digital information across hundreds of kilometers of near vacuum with losses measured in mere decibels. The physics of radio propagation in this rarefied environment creates conditions that radio engineers find both advantageous and challenging. Lower atmospheric density means reduced scattering of electromagnetic waves, allowing precise communication links between surface assets and orbital relays. Yet the same thin atmosphere that enables clear radio transmission also fails to provide the ionospheric reflection properties that enable long-distance radio communication on Earth. Martian radio waves travel in straight lines, limited by the planet's curvature and the line-of-sight constraints that govern all electromagnetic radiation. Mission controllers on Earth receive these Martian radio signals as faint whispers detected by massive dish antennas scattered across multiple continents. The Deep Space Network maintains constant vigil for these transmissions, using 70-meter parabolic reflectors that can detect signals as weak as 10 to the minus 16th watts power levels, so infinitesimal that the energy received during an entire communication session equals less than the kinetic energy of a falling snowflake. Yet, within these whisper-soft signals lies detailed information about wind speeds, rock compositions, and atmospheric pressures measured on a world 40 million kilometers away. The time delay inherent in interplanetary communication creates a unique rhythm for Mars exploration. Radio signals, traveling at the speed of light, require between 4 and 24 minutes to traverse the distance between Earth and Mars, depending on the relative positions of the planets in their orbits. This delay means that every command sent to a Martian rover must be planned hours in advance, and every response from the rover arrives as a message from the past. Mission operators work within this temporal disconnect, planning sequences of activities that account for the inevitable communication delays. During superior conjunction, when Mars passes behind the Sun from Earth's perspective, solar plasma interferes with radio transmissions for periods lasting up to 2 weeks. The corona's charged particles scatter radio waves in unpredictable patterns, corrupting digital data and rendering communication impossible. Mission planners schedule these periods as communication blackouts, programming spacecraft to operate autonomously while cut off from Earth's guidance. the rovers enter a form of hibernation, performing only essential maintenance tasks while waiting for the planet's orbital motion to restore the communication link. The radio spectrum allocated for deep space communication represents a carefully negotiated resource shared among space agencies worldwide. Mars missions typically operate in the X-band frequency range, using radio waves with frequencies near 8 GHz chosen for their optimal balance between atmospheric penetration and antenna efficiency. At these frequencies, the wavelengths measure approximately 4 centimeters, requiring precise pointing accuracy to maintain communication links across interplanetary distances. Atmospheric conditions on Mars create subtle but measurable effects on radio wave propagation that provide scientists with indirect measurements of meteorological conditions. Changes in atmospheric pressure alter the refractive index of the thin air, causing minute variations in signal arrival times that can be detected by atomic clocks accurate to nanoseconds. These timing variations, called group delay measurements, allow researchers to monitor atmospheric density changes caused by dust storms, seasonal temperature variations, and the daily cycle of atmospheric heating and cooling. The Doppler effect manifests dramatically in Mars-Earth radio communications, as the relative motion between the planets can exceed 20 kilometers per second during certain orbital configurations. This relative velocity shifts radio frequencies by amounts large enough to require constant correction by ground-based receivers. The frequency shifts provide precise measurements of planetary velocities and orbital parameters, contributing to our understanding of solar system dynamics and the subtle gravitational influences that perturb planetary motion over geological time. Interference patterns created by signals reflecting off the Martian surface provide information about surface composition and roughness. Radio waves transmitted from orbiters toward the surface produce echoes that return to the spacecraft after bouncing off rocks, dust, and ice deposits. The strength and polarization characteristics of these reflected signals reveal details about surface materials that complement direct observations from cameras and spectrometers. Smooth surfaces produce strong, coherent reflections, while rough terrain scatters radio energy in multiple directions, weakening the returned signal. The electromagnetic environment around Mars differs fundamentally from that surrounding Earth due to the planet's lack of a global magnetic field. Without magnetospheric protection, Mars's upper atmosphere interacts directly with solar wind particles, creating a complex plasma environment that affects radio wave propagation in ways still being studied. High-energy particles from the Sun create ionization in the upper atmosphere that can cause signal fading and distortion, particularly during periods of enhanced solar activity. Radio astronomy observations conducted from Mars' orbit offer unique perspectives on cosmic radio sources, as the planet's position in the solar system provides a different vantage point for studying distant galaxies and pulsars. The absence of radio frequency interference from human activities makes Mars an ideal platform for sensitive radio observations, though no dedicated radio telescopes have yet been deployed to the planet. Future missions may take advantage of Mars's radio-quiet environment to conduct astronomical observations impossible from Earth's increasingly crowded electromagnetic spectrum. The polarization characteristics of radio waves change as they pass through Mars's atmosphere, providing information about atmospheric composition and the presence of suspended dust particles. Linear polarization becomes partially converted to circular polarization through interactions with asymmetrical molecules and charged particles, creating measurable signatures that reveal atmospheric conditions along the radio path. These polarization measurements complement other remote sensing techniques for monitoring atmospheric dynamics and composition. Digital encoding schemes used for Mars communication employ sophisticated error correction algorithms designed to maintain data integrity despite the challenging propagation environment. Reed-Solomon coding and convolutional encoding add redundancy to transmitted data, allowing ground receivers to reconstruct perfect copies of transmitted information even when portions of the signal are corrupted by noise or interference. The overhead required for this error correction reduces the effective data transmission rate, but ensures reliable delivery of scientific observations across interplanetary distances. The power requirements for Mars communication systems reflect the fundamental challenge of transmitting information across astronomical distances. Rovers typically transmit at power levels of only a few watts, comparable to a small light bulb, yet sophisticated antenna designs and signal processing techniques enable reliable communication with Earth. The inverse square law governing electromagnetic radiation means that doubling the distance between transmitter and receiver reduces signal strength by a factor of 4, creating exponentially increasing power requirements for communication across the solar system. Relay communication through Mars orbiters provides an elegant solution to the power limitations of surface-based transmitters. Rovers can communicate with orbiting spacecraft using relatively low power, while the orbiters use larger antennas and higher transmission power to relay data to Earth. This two-hop communication architecture maximizes the amount of scientific data that can be returned from the Martian surface, while minimizing the mass and power requirements of surface vehicles. The nucleus of 3I Atlas begins its gradual awakening as solar radiation penetrates the outermost layers of primordial ice that have remained undisturbed since the comet's formation around a distant star. At its current distance from the Sun, approximately 4 astronomical units beyond the orbit of Mars, the solar flux reaching the comet's surface measures only 6% of the intensity experienced at Earth's distance. Yet even this attenuated radiation proves sufficient to initiate the molecular processes that will transform the dormant wanderer into an active comet. Water molecules embedded in the crystalline ice structure absorb infrared photons that carry just enough energy to break hydrogen bonds holding the solid matrix together. The transition from solid to vapor occurs directly, bypassing the liquid phase entirely in the near vacuum conditions surrounding the nucleus. This sublimation process releases individual water molecules at velocities approaching 500 meters per second, fast enough to escape the comet's weak gravitational field and form the beginnings of a tenuous coma around the nucleus. The rate of outgassing remains almost negligible at this early stage, perhaps 10 grams per second across the entire surface of the 2-kilometer nucleus. To put this mass loss in perspective, 3I Atlas loses material at roughly the same rate that a small household humidifier adds water vapor to room air. This gentle awakening ensures that the comet will retain most of its original mass during its passage through the inner solar system, preserving the ancient materials it carries from its birth system for eventual return to interstellar space. Spectroscopic observations detect the first traces of water vapor, carbon monoxide, and carbon dioxide in the expanding coma as these molecules absorb and re-emit solar ultraviolet radiation at characteristic wavelengths. The relative abundances of these species provide clues about the temperature and chemical conditions that prevailed when the comet first condensed from the protoplanetary disk around its parent star. Carbon monoxide, which sublimates at lower temperatures than water ice, appears first in the spectroscopic signatures, followed by water vapor as solar heating penetrates deeper into the nucleus. The coma itself represents one of the most tenuous atmospheres in the solar system, with particle densities so low that individual molecules travel hundreds of kilometers before colliding with another molecule. In this collision-free environment, the gas expands radially outward from the nucleus at constant velocity, forming a spherical envelope that grows larger with each passing day. The boundary between the coma and the surrounding interplanetary medium remains completely invisible to the naked eye, detectable only through sensitive spectroscopic techniques that measure the faint glow of excited molecules. Thermal models of the nucleus suggest that heat conduction into the interior proceeds slowly through the loose aggregate of ice and dust that comprises the comet's structure. The low thermal conductivity of this material, similar to freshly fallen snow, means that solar heating affects only the outermost few centimeters of the surface. Beneath this active layer, the bulk of the nucleus remains at temperatures near absolute zero, preserving chemical compositions that may predate the formation of our solar system. The sublimation process creates microscopic jets of vapor that escape preferentially from areas where the surface composition favors rapid outgassing. These jets, invisible except through their effect on surrounding dust particles, create non-gravitational forces that slightly alter the comet's trajectory. The rocket effect of escaping gases accelerates the nucleus by amounts measured in millimeters per second, but these tiny velocity changes accumulate over months to produce positional shifts detectable by precise astrometric measurements. Dust particles embedded within the sublimating ice become entrained in the expanding gas flow and carried away from the nucleus at velocities determined by their size and the local gas density. The smallest particles, with dimensions measured in micrometers, achieve velocities approaching those of the gas molecules themselves. Larger particles, millimeters in diameter, move more slowly and may fall back to the surface in regions where outgassing rates remain low. This size-dependent sorting process creates compositional variations in the coma that reflect the heterogeneous structure of the nucleus interior. The isotopic composition of the outgassing provides the most direct evidence for the comet's extrasolar origin. The deuterium to hydrogen ratio in water vapor from 3I Atlas differs measurably from that found in solar system comets, suggesting formation conditions distinct from those that prevailed in our protoplanetary nebula. These isotopic signatures represent chemical fossils of nucleosynthetic processes that occurred in the stellar environment where the comet originated, preserved across millions of years of interstellar travel. Radio observations at millimeter wavelengths detect rotational transitions of carbon monoxide and other molecules in the coma, providing measurements of gas temperature and expansion velocity that complement optical spectroscopy. The line profiles of these molecular transitions reveal systematic velocity patterns that indicate non-uniform outgassing across the nucleus surface. Some regions appear more active than others, possibly due to compositional heterogeneities or topographical features that focus solar heating into confined areas. The magnetic field embedded in the solar wind begins to interact with the ionized component of the coma as outgassing rates increase with continued solar heating. Ultraviolet radiation from the sun photoionizes a small fraction of the neutral gas molecules, creating charged particles that respond to electromagnetic forces. The interaction between these newly created ions and the solar wind magnetic field will eventually form the characteristic ion tail that makes comets visible to observers on Earth. Though at this early stage the ionization rate remains too low to produce observable tail formation. Ground-based telescopes equipped with adaptive optics systems strain to resolve structure within the growing coma, but the comet's distance and the inherent faintness of the outgassing make detailed observations challenging. The coma appears as a slightly fuzzy, star-like point in even the largest telescopes, distinguishable from background stars only through its gradual motion against the stellar background and the subtle spectroscopic signatures of molecular emission. Professional astronomers coordinate observation campaigns to track the comet's development as it approaches perihelion, knowing that this may represent their only opportunity to study an active interstellar comet. The dust-to-gas ratio in the early coma provides insights into the formation environment of the comet's parent system. Observations suggest that 3I Atlas contains less dust relative to ice than typical solar system comets, possibly indicating formation in a region where dust grain growth proceeded differently than in our own protoplanetary disk. This compositional difference, if confirmed by continued observations, would represent direct evidence for variations in planet-forming processes around different stars. Computational models of coma dynamics predict that the expanding gas envelope will reach maximum size when the comet achieves its closest approach to the Sun. At that point, the coma may extend several 100,000 kilometers from the nucleus, larger than the distance between Earth and the Moon, yet containing less mass than a small mountain. The contrast between the vast apparent size of an active comet and its tiny actual mass demonstrates the exotic physics of matter distribution in the near-vacuum conditions of interplanetary space. The comet's increasing activity marks the beginning of a transformation that will peak during its passage through the inner solar system before gradually declining as it recedes toward the outer planetary region. This cycle of activation and dormancy, driven entirely by the changing intensity of solar radiation, represents one of the most predictable yet spectacular phenomena in astronomy, the rebirth of an ancient wanderer as it briefly tastes the warmth of an alien star. The Great Canyon system of Valles Marineris stretches across Mars' equatorial region like a geological scar that refuses to heal, extending over 4,000 kilometers from east to west, a distance that would span the entire continental United States. Within this vast network of interconnected chasms lie the fossilized remains of ancient river channels, carved by flowing water during an epoch when Mars possessed a thicker atmosphere and temperatures warm enough to sustain liquid water on its surface. These channels now lie silent beneath layers of rust-colored regolith, their carved geometries preserved in stone as testimony to the planet's more hospitable past. The tributary patterns etched into the canyon walls follow the mathematical principles of dendritic drainage that govern river systems throughout the solar system. Smaller channels converge into larger ones with the same branching angles and length ratios found in terrestrial watersheds, demonstrating that liquid water once obeyed the same physical laws on Mars that govern terrestrial hydrology. The preservation of these patterns in solid rock creates a form of geological photography, capturing the flow dynamics of ancient Martian rivers in permanent mineral form. High-resolution orbital imagery reveals the intimate details of these fossilized waterways with clarity approaching that of aerial photography. Individual boulders transported by ancient floods remain visible on canyon floors, their positions marking the final moments of flowing water that ceased billions of years ago. The spacing and size distribution of these rocks follow patterns consistent with hydraulic sorting, where flowing water naturally segregates sediments according to size and density. Larger boulders cluster in areas where channel constrictions created high-velocity flows, while finer sediments accumulated in broader reaches where water velocities decreased. Spectroscopic analysis of the channel deposits reveals mineralogical signatures consistent with prolonged water-rock interaction under conditions dramatically different from the current Martian environment. Clay minerals identified within the ancient sediments require liquid water for their formation. Yet these same minerals remain stable under current Martian conditions, serving as chemical fossils of a time when the planet's surface chemistry operated in an entirely different regime. The presence of hydrated sulfates and carbonates further confirms that these channels once carried water with dissolved minerals similar to terrestrial groundwater. The depth and width of the largest channels indicate discharge rates comparable to major terrestrial river systems during peak flow conditions. Hydraulic modeling based on channel geometry suggests that some ancient Martian rivers carried water volumes exceeding those of the modern Amazon River, moving billions of liters per second across a landscape that now receives less annual precipitation than the driest deserts on Earth. These massive flows likely persisted for thousands of years, sufficient time to carve the complex channel networks visible in satellite imagery. The termination points of many channel systems occur in topographic basins that show evidence of having contained standing water for extended periods. Sedimentary deposits in these ancient lakebeds display the horizontal layering characteristic of quiet water deposition, contrasting sharply with the chaotic boulder fields found in the channels themselves. Orbital radar has penetrated these sediment layers to reveal buried channel networks that extended beneath the lake surfaces, suggesting that some Martian lakes were fed by groundwater springs in addition to surface runoff. The timing of channel formation coincides with a period in Martian history when the planet's obliquity, the tilt of its rotational axis, differed significantly from its current 25-degree inclination. Computer simulations of Martian climate during periods of higher obliquity show that increased seasonal temperature variations could have driven sufficient atmospheric circulation to transport water vapor from polar ice deposits to equatorial regions, where it precipitated as snow and rain. The correlation between calculated climate conditions and observed geological evidence suggests that orbital mechanics played a crucial role in determining when liquid water could exist on the Martian surface. Crater counting studies of the channel networks provide estimates of their formation ages that cluster around 3.5 billion years ago, during the transition between the Noachian and Hesperian geological periods. This timing corresponds to a fundamental change in Martian atmospheric evolution, when the planet's magnetic field weakened sufficiently to allow solar wind erosion of the atmosphere. The cessation of channel-forming activity coincides with this atmospheric loss, suggesting a direct connection between planetary magnetic field strength and surface water stability. The preservation of these ancient channels requires that erosion rates on modern Mars remain extraordinarily low compared to those on Earth. Calculations based on current dust storm activity and chemical weathering rates suggest that features exposed on the Martian surface erode at rates of only a few nanometers per year, 10,000 times slower than typical terrestrial erosion rates. This remarkable preservation allows geological features billions of years old to remain visible with minimal modification, creating a planetary museum of ancient surface processes. Some channel systems show evidence of multiple episodes of water flow separated by periods of dormancy lasting millions of years. Younger channels sometimes cut through older, partially filled valleys, indicating that conditions suitable for liquid water returned episodically throughout Martian history. The cyclical nature of these flow episodes may reflect long-term variations in the planet's orbital parameters or sporadic volcanic activity that temporarily thickened the atmosphere through outgassing of water vapor and carbon dioxide. The chemistry of minerals found within channel deposits provides constraints on the composition and temperature of ancient Martian water. Iron-bearing minerals show oxidation states that require the presence of dissolved oxygen, while the absence of certain clay minerals that form only in highly acidic conditions suggests that early Martian water was relatively neutral in pH. These chemical indicators paint a picture of ancient Martian surface water that would have been hospitable to life forms similar to terrestrial extremophiles that thrive in cold, alkaline environments. Thermal infrared observations reveal that channel floors retain heat differently than surrounding terrain, creating subtle temperature variations that persist throughout the Martian day-night cycle. These thermal signatures result from differences in rock size distribution and mineral composition between channel deposits and the surrounding bedrock, allowing orbital instruments to map ancient river systems even when they are partially buried by dust. The thermal mapping technique has revealed previously unknown channel networks in regions where optical imagery shows little surface expression. The scale of water flow required to carve the largest channels implies the existence of substantial underground reservoirs that could supply sustained discharge over geological timescales. Subsurface ice deposits discovered by ground-penetrating radar represent possible remnants of these ancient aquifers, now frozen but preserving chemical and isotopic signatures of the water that once flowed across the Martian surface. The spatial distribution of these subsurface ice deposits correlates with the locations of major channel systems, supporting the hypothesis that underground water sources fed many of the ancient rivers. Current models of Martian atmospheric evolution suggest that the transition from a water-rich to a water-poor planet occurred gradually over hundreds of millions of years, with brief periods of increased atmospheric density caused by large impact events or volcanic eruptions. During these temporary atmospheric thickening episodes, conditions may have briefly returned to states that allowed liquid water to flow across the surface, carving new channels or reactivating existing ones. The geological record preserves evidence of these episodic returns to more clement conditions in the form of younger channel systems that cut through older, degraded valleys. The silence that now characterizes these ancient waterways represents one of the most profound transformations in planetary history. The transition of an entire world from conditions that supported flowing water to the frozen desert that Mars has remained for billions of years. Yet the channels themselves persist as monuments to that lost hydrological cycle, their carved geometry speaking of processes that once operated under alien skies now vanished into the deep past. The celestial mechanics governing the motions of both Mars and 3I Atlas operate according to principles so precise that their positions can be calculated decades in advance, with accuracy measured in kilometers across distances spanning astronomical units. This mathematical predictability emerges from Newton's law of universal gravitation, which describes how every particle of matter in the universe attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. The orbital trajectories of both objects trace paths through space that represent solutions to this fundamental equation, executed with the unwavering consistency of cosmic clockwork. Mars follows an elliptical orbit around the Sun with an eccentricity of 0.09355, making its path noticeably more elongated than Earth's nearly circular trajectory. This orbital shape means that Mars experiences significant variations in solar heating throughout its 687-day year. Receiving 45% more solar energy at perihelion than at aphelion, the gravitational influence of Jupiter, with its mass exceeding that of all other planets combined, produces subtle perturbations in Mars's orbit that accumulate over centuries to create measurable changes in orbital parameters. These perturbations follow patterns so regular that astronomers can predict the planet's position thousands of years into the future. The comet 3I Atlas traces a hyperbolic trajectory that represents the mathematical signature of an unbound orbit, a path that curves around the Sun once before extending to infinity. Unlike the closed elliptical orbits of planets, which repeat endlessly in cycles, the comet's hyperbolic path is unique and irreversible. The mathematical parameters that define its trajectory, semi-major axis, eccentricity, inclination, and argument of periapsis encode the comet's entire history of gravitational encounters since it entered the solar system. Each parameter reflects the cumulative influence of every massive body the comet has approached during its inward journey. Orbital mechanics calculations require the integration of gravitational forces from all significant bodies in the solar system, creating a complex mathematical problem known as the n-body problem. While no analytical solution exists for systems containing more than two gravitating bodies,